Good morning, everyone. So we're going to pick up from this slide that we mentioned that we would start from this time on Lecture on Wednesday. If you didn't recall how to get these slides, if you wanted to follow along with the slides, they're in Carmen. Go to Modules, go to Lecture Slides, and then you can find the PDF for Chapter 1. So we're just talking about some basic terminology here to start off today. So atoms, I think we know this, they're our basic building block of matter. All atoms are comprised of one of the different elements that we can find on the periodic table. I was actually looking at this periodic table and thinking we really need to get a new one. If you didn't know this, all 118 elements that would fit into the table have thus far been discovered. If you go past uranium, element 92, those are the elements that no longer naturally occur on Earth because they're all so reactive that they've fallen apart and decayed into smaller elements over the course of time. But we can synthesize, and not me, but scientists can synthesize some of those elements, and some of the really heavy elements, like getting towards like element 118, the largest known element, they're colliding particles and maybe forming one or two of those elements just to prove that it existed for a very short fraction of a time. In fact, physicists are still trying to synthesize even larger elements. They're working on element 119 and larger kind of as we speak. But element 92 and smaller, practically speaking, those are the elements we're going to find in nature, and obviously a lot smaller in terms of the elements of the ones that we most commonly work with. So a few of the elements I would just recommend making sure the symbol to name to symbol are recognizable. I'm never going to give you a periodic table quiz and have you lay out exactly where the elements are, but I think it's just really useful if I say NaCl, I think most of you know that that's sodium chloride, but just to make sure that we don't get caught up in not knowing some of the symbols, look at the first row, that's the alkali group. We'll define some of the group properties in chapter 2, a little bit more in chapter 7. But the first group, lithium, sodium on downward, I'd recommend knowing name to symbol, symbol to name. Same thing with beryllium, magnesium, calcium, strontium, barium. Just knowing the symbol versus the name. If I give you the name, know the symbol, or be able to find this symbol on a periodic table. Or if I give you the symbol, be able to know what name it is to match up with the name that you might need to find. And then the first 4 rows or so are pretty common in examples. So if you go through the entire first 4 rows, if you then go through the non-metal side, the right side of our periodic tables mostly are non-metals. The halogen group, fluorine, chlorine, bromine, iodine, really common in examples, but also pretty straightforward symbols. The noble gases we use in a lot of examples, so knowing their name to symbol, symbol to names are useful as well. And so then a few of the larger elements like silver, gold, mercury, tin, lead, those come up a lot. Some of them aren't exactly the most obvious name, like lead versus Pb isn't maybe something you've seen in a while, but just to make sure that if we're giving examples of naming and we say what's like lead chloride, that you're not confused on why that would be PbCl2. So again, not really memorizing the full layout of the periodic table, but just recognizing the symbol name pairs for some of the common elements that we'll see in a lot of examples. So what's a compound? A compound is when we have 2 or more different elements that are chemically bonded together. And there's some different types of chemical bonds that we have probably seen before. So I'm going to give 2 quick examples of some different type of compounds. So we have, of course, water is a really obvious example of a compound. We have 2 different elements, hydrogen and oxygen, present in that compound. And then this is what we would call a covalent bond, that line that we write between H and O, that's a covalent bond. And we get into the nature of covalent bonding in a few different parts of the class. We'll get into just naming and recognizing some compounds at the end of chapter 2. We'll get into sketching Lewis structures. If you're wondering, should we be writing electron pairs around O? We'll talk about that in chapter 8. And then 3-dimensional shapes in chapter 9. So we have a good amount of material that we'll see in terms of predicting what a Lewis structure might look like. So I'm not showing the structures that you predict other molecules' Lewis structures at this point, but just so that we kind of get the idea that that's a chemical bond. That little line we write between H and O, that's what we mean by one type of bond being a covalent bond. And then in sodium chloride, that we have a different type of bond that goes on, but that would still be a compound. Sodium chloride is a compound between sodium and chlorine. And then we call that the ionic bond because we have these charges that develop on these ions, and so we call this bond here the ionic bond. There might be one other key type of bonding that we talk about later, which is metallic bonding. I'm not going to bring that up today with an example or sketch that out. But iron solid, what links the iron atoms is what we call the metallic bond. So there's bonding in solid metals. That's what's holding those atoms together, is a different type of bond altogether from these two called metallic bonding. So there's like three sort of primary types of forces of attraction that are holding atoms together. Iron itself, though, if we just had iron solid, if I was looking at this and saying, well, what's the bonding here? Metallic, we'll describe that way later in the course, maybe in the chapter 12s, not until we're really understanding the bonding in that type of compound. But it's also like we wouldn't be calling iron solid, we wouldn't be calling that a compound because that's just one element. So this isn't a compound, that would just be an element. So this here would not be a compound. So compounds, we need at least two elements. And so then we get into chemical and physical changes. Sometimes chemical reactions are obvious if we can actually like write the chemical reaction out. Like we saw the H2 plus O2 reaction producing water in terms of a reaction written out on our previous slide. So if we can imagine a reaction written out where we have bonds being changed, we have atoms that are now bonded with different elements, we know a chemical reaction's occurred under that situation. If you can imagine, like one maybe easy thought for a chemical reaction is, can you undo what was done very easily? Like if we break an egg or something, we're doing a lot of reactions. If we cook an egg, we're doing reactions that we're not just going to easily flip a switch and undo. If we blow up that balloon, we're not just flipping a switch and having it reform back together. But if I melt an ice cube, I can put it back in the freezer and refreeze it. So the melting of an ice cube, the changing of the phase of a substance, is something that we just call a physical change. A chemical change requires a change in the chemical environment of the atoms. It requires a change of the bonds that are made. Physical reactions just lead to changes in phase, changes in temperature, changes in pressure, without changing the actual underlying bonding nature between the atoms in the substance. And then another key set of terminology that we introduced in chapter 1 is intensive versus extensive properties. And I think there's a really important reason here is just to try to define the intensive property is the quantity independent property. And this is the characteristic property. Like this is the property that if you have 10 grams of water or if you have 1,000 grams of water, the melting point and the boiling point's the same. So the melting point and the boiling point don't depend on how much sample you have. They are characteristic properties of the substance itself. So a boiling point, a melting point, the ratio of the mass to volume for a given substance is a characteristic property. A characteristic property is usually something that, if you look at an entirely different substance, like say ethanol, ethanol has a different melting point and boiling point from water. Ethanol has a different density than water. So different properties tend to have different characteristic properties. Those characteristic properties are generally in that category of being a quantity independent quantity, that intensive property. Then an extensive property is just one that tells you something about how much of the substance you have. So you have 100 grams of water. The mass of the sample is obviously quantity dependent. Now, you may say, if you know you have 100 grams of water, you probably know you have about 100 milliliters of water. But that's just because you happen to know the density, you know the characteristic property of water. If you had ethanol, if you had 100 grams of water, it turns out the density of ethanol is about 0.789, I think, grams per milliliter. So it's not precisely or close to 1 gram per milliliter like water is. You're not going to have 100 milliliters. You're going to have a different volume. But you could calculate the volume. We'll get into density calculations later in chapter 1. We could calculate the volume if we knew the density and knew the mass. Pretty easy problem to figure out. But the fact that we can know how much mass versus how much volume is there doesn't change the fact that the mass itself is a quantity dependent value. The volume of a substance, it kind of means like you can have 5 mils of water, you can have 25 mils of water. That's an extensive property. It's just simply a quantity that is telling you how much of the substance that you happen to have. It turns out heat is also a quantity dependent value. So if you have a lot of something, it can hold a lot of heat, but if you have the same substance, a little bit of it, it can only hold a little bit of heat. So heat in and of itself is a quantity dependent and extensive property of a substance. And we'll talk about how that maybe comes into play when we get to chapter 5 later. Okay, so let's think about water for a minute. So let's imagine we just have, let's say, a sample of water. Let's say we have 30 milliliters of water in like a container. And so let's try to classify each property as intensive or extensive, and then try to classify that as a physical or some sort of chemical property of the substance. So just the very fact that we know we have 30 milliliters of water, this volume here, the 30 milliliters, that property, is that intensive or extensive? extensive. Yeah, it's just telling us how much we have. And then obviously no chemical reactions taking place. That's just a physical property of the sample. There's no chemical property embedded in how much just simple water that we have, right? So that would just be a simple physical property. So if we say the density, we say, okay, we have a new property. We're telling you that the density of water is 1.00 grams per milliliter. If you're savvy, you might know the density of water is temperature dependent. So if you get very precise, it's not precisely 1.000 out to infinity, but about 1 gram per milliliter for the density of water. What type of property is that? Intensive or extensive? That's the intensive property, because that is the characteristic density of water. If we had 50 mils of water, we'd have the same density. If we had 70 mils of water, we'd have the exact same density. So density doesn't change with how much quantity of water that we have. And then chemical versus physical, you'd probably still say that's a physical property. That's really not telling us anything about a chemical change. So that's just some sort of a physical property of water. What about a boiling point? Characteristic, property, intensive or extensive? Yeah, so still in that category of being an intensive property. And then this is an interesting one because we can actually, and we sometimes do write this out as a reaction. We might write out water liquid going to water gas. We sometimes write that out as a chemical reaction, but it's really not a chemical reaction because we're not breaking and changing the bonds between the atoms in water. We start with water, we end with water. We have water boil, we can recondense it back to water liquid. So even though this really does maybe in some ways look like a chemical reaction, this is really best described as being a physical change. So physical reaction, physical change going on with a phase change. So again, sometimes confusing because you may say, and then when we get to chapter 5, we start writing out reactions of things that are taking place and noting their heat changes. There's a heat change associated with this reaction. We can write it out like a chemical reaction, but really it's best described as being a physical reaction. And then I was trying to come up with something like with just a simple fact of water. It turns out if you had that 30 ml sample of water, that if you just wanted to take the liquid water and just like blow it up into atoms and just have it, and which is really hard to do because water is really quite stable. So you're not just going to put a match to water and have it explode or anything. But if you wanted to somehow try to remove all the atoms from the water molecule itself, that would take 969.2 kilojoules per mole for the water. So that's how much energy it would take to atomize, to go from liquid water into just H atoms and O atoms fully separated from each other. And so is that property, is that atomization energy, does that look like a physical or chemical property? Or that looks like a chemical property, right? Because that's a chemical reaction. So our chemical reaction here is we're taking the liquid water, the bonds between the H and the O, and then we're blowing this up into 2 hydrogen atoms plus an O atom. The chemical reaction writing itself, don't get too caught up with that. We'll talk about chemical reactions in chapter 3 in more detail into chapter 4, but it's just kind of showing us we have a change of the bonding nature in the molecule of water. So that's a chemical change, chemical reaction. And then the property itself, this is maybe a little confusing too in terms of if I had more water, because I said it was 962 kJs per mole of water, mole's the quantity of water. So because it's like kJs per mole, that quantity would be quantity independent. So this goes to an intensive property. If I had worked out how many moles of water were in the sample, and then for that sample, so I guess this question, I started it off my explanation a little bit off. So I had said if we blew up all the water molecules in our 30 ml sample, that's actually not what this question's saying or what this dash is saying. It's saying just the atomization energy of water in and of itself is 969.2 kJs per mole. So just a property of water itself, not a property of that 30 ml sample. This is a property of water as a whole. And so if we have more or less water, it's going to have that same atomization energy. So just a couple examples to try to hopefully get us to understand the difference between intensive, extensive properties and physical and chemical changes. This slide here is just showing us a couple different forms of matter where on box A, we're looking at just where we have atoms of a given element. There's only one group of elements, that's the noble gases, that exist naturally as a gaseous atom. where the atoms aren't somehow bonded together to form some type of molecule, or maybe in some sort of solid phase, like mostly our metals or solids in their natural state. So helium, neon, argon, krypton, xenon, radon, those atoms exist as just a monoatomic gas in their natural state at standard temperature and pressure here on Earth. And so this might be describing a sample like helium, where we have helium atoms in a gas sample. If we had oxygen, oxygen is going to bond with itself into O2. So oxygen or maybe nitrogen might look something like this. So this might be demonstrating what a nitrogen gas sample looks like. So gases are in more detail discussed in chapter 10, but gases are just independent particles. You have independent particles of the gas just moving around a container in sort of constant motion. So helium, we have a container would have a lot more than 6 atoms of helium, but if you imagine a helium cylinder, a bunch of individual atoms of helium all independently moving around. If you imagine a cylinder or a container of nitrogen gas, you'd have 2 nitrogens bonded together, independently moving around the container, and a bunch of those making up your container. If you had a container, say, of ammonia, maybe it looks something like this, where you have NH3 molecules, maybe you have a gas sample of NH3. And the reason why I'm kind of specifying the gas phase here is that these atoms look kind of far away. They're not really stuck together. They don't seem to be solids or liquids. We'll see a slide in a moment where water, comparing its solid versus liquid versus gas phase, liquid molecules would be closer together, solid would be kind of almost locked into shape. So the difference here between monoatomic gas for helium is that's just an atom, that's an element for box A. We have molecules in N2, but N2 is not a compound because there's only one element present. Then in NH3, we could look at NH3 and say that that's obviously a compound because we have 2 different elements present. So now we have a compound because the 2 different elements, but then is existing as a molecule, so it's a molecular compound, as opposed to NaCl, which would be like an ionic compound. So we see a lot of molecular compound examples in this class. And so that's molecules of a compound. And then one other mixture shown is where we just have all those gases intermixed together just for some sort of a mixture. And so we can also have mixtures of compounds. And this slide isn't meant to really show all the possibilities. We're not looking at other phases. We're just kind of looking at gases. And we're comparing here having a mixture where we can have multiple components mixed together. And then these appear to be what we would call homogeneous. We'll contrast that in a moment with what we mean by heterogeneous mixtures. But that's just where all the gases are mixed perfectly. And so they're just mixing around kind of randomly in random motion. We don't have like a helium layer at the bottom. We don't have like a nitrogen layer in the middle and ammonia at the top or anything like that. We don't have a separation of phases. In fact, with gases, you really can't have a heterogeneous mixture like you can with like salad dressing where the layers separate. Gases are just always in motion, so they're always going to mix together for a homogeneous mixture. Now this is the slide I was alluding to that compares like different phases. And so whenever we show like a atomic box, we're trying to show like a molecular picture. When I'm showing a gas, I'm going to show the particles kind of separated from each other. If I was showing you a liquid, I'm going to put the molecules really close together, but not in any kind of particular pattern, because like the molecules are still tumbling around. Like liquid water would have water molecules, instead of in the gas phase bouncing around kind of far away from each other, they're now closer but still independently moving, still fluid in their motion. And then when they go to ice, they just kind of lock into a shape. Now, if you look at an ice structure, those molecules aren't permanently stuck. You might be permanently frozen if you go all the way down to like 0 Kelvin towards absolute 0. You might see the atoms really start to move very, very slowly. But even in ice, the molecules are still going to be like fluctuating a little bit. So they're never really perfectly still, but they're aligned much more closely. So when you're looking just at a diagram, you can kind of see we're trying to show a solid whenever the particles are really in a almost perfect arrangement relative to each other. If they're close but random, that's just showing you the liquid state. And then far apart, that's showing us the gaseous state. And so when we're going from solid to liquid to gas, again, just to reinforce, and I don't think I necessarily need to reinforce this again, but just physical changes going through here because we can go back and forth. And most substances can undergo a freezing, then we can melt, then we can boil and go back and forth. Some things do get confusing. Like for example, you put sugar in butter on the stove and you heat it up. Does the sugar melt? Or even if you just don't even put the butter, just put sugar in a pot and you heat it up, you may have done this before. It doesn't exactly melt into like a liquid phase that you can then refreeze back into ordinary sugar. It starts to decompose and break apart. And so like something like cooking of an egg, you know you're doing a chemical reaction when you start with something, and then it like you heat it up, and then when you let it cool down, it doesn't go right back to where you were before. And so whenever you heat up sugar and it changes into like almost like a caramelized color, and then you sort of start to make caramel, you know that some chemical reactions had to have occurred. You may not know what the chemical reactions are, you just know that you're not going back to ordinary sugar when you let that mixture cool. So not every substance can undergo an easy transformation of all these phases, but if you can, those are just simple physical transformations. Okay, so now how can we understand the composition of matter? Now this diagram, we can't always, like I can't just like look at a sample and necessarily go through this flowchart. Like if somebody handed me a sample that was just a clear liquid, I could look at that clear liquid and assess the question, is it uniform throughout? Like the uniform throughout is usually like when I'm looking at a piece of matter, does it all look the same? Or if I look at the matter, do I see a layer on the top and a layer on the bottom? So if I see two different layers, then that's the heterogeneous mixture. So heterogeneous mixture is where I'm seeing two different phases. I'm seeing, like if I'm looking at a solid, I'm kind of seeing one color on one side of the solid, a different color on the other side. Maybe I'm looking at like a rock where I see a different color on one side versus a different color on the other side. That's heterogeneous. If I'm looking at an oil and vinegar mixture that's separated into one layer and the other layer, then that's a heterogeneous mixture. Whenever we see a mixture and I'm like, oh, that's like just a clear substance, or it's just like a white powder, nothing looks different on one side versus the other side of the substance, then that's homogeneous. So that just means it looks the same, appears the same. So you can usually assess this question with your eyes. So we can usually look at a sample and tell if it's uniform throughout just by simple inspection. Then when we say, okay, I know something's homogeneous, like it's a clear liquid, is it just one substance or are there more than one substance in that liquid? So let's say you could have handed me pure water and it's just one substance, or you could have handed me salt water, or you could have handed me sugar water, or a variety of things that are dissolved in water that I would never know by naked eye. And so the question here, does it have a variable composition? This is something that you need some sort of chemical knowledge or tool. So we can't see this with our eyes. So we can't assess the variable composition question just by looking at a sample, unless you have laser vision, which if you do, that'd be cool. But unless we can literally see at the molecular level, we're never gonna know if the sample has one substance or if it has multiple substances. So we have to either do a test, have to know how the sample is constructed. If I just said, okay, like what is in this? And you said, well, I dissolved the powder into the water. I could be, okay, well, clearly that's in a mixture. So if I know that you put two or more substances into the mixture, then that's a homogeneous mixture. If we then somehow do a test or we're looking at a molecular level and I see only the same type of compound in the sample, then that would just be a pure substance. And so maybe it's just pure water if I know there's no other substance present from either some chemical test or just from how the sample was put together. Now let's get to another question. If somebody said it's pure water, how many of you would say, well, no water can be 100% pure? So when we say pure in this class, we're meaning like 99% plus the intended substance. So nothing is really ever going to be 100%, or it's going to be very hard to get the 100.00000% exactly pure. So when I say a sample is pure water, it's like mostly water. There might be some contaminants still in it. There might be some small traces of other things within it. And so then once we know we have a pure substance, let's say, and we then say, does it contain more than one kind of atom? This is something that we're generally going to assess by chemical reaction. And so, but not by our eyes directly. And so what we're going to try to do with our substance is we're going to try to break it apart into smaller components. And this is really how alchemists in the 16, 17, 1800s were determining what the different elements were from a very early time. And some of the first elements discovered were things like iron, things that were present in ores. So different heavy metals were the things that were being the first elements to be discovered, because we were just heating up, or scientists then were heating up sort of rocks and minerals that they were coming across and just trying to break them down. And they were finding, well, these things keep breaking down into this one thing that we can't break down further. So the thing that we can't break down further must be an element. And then they would classify that element based on some of its properties. And then from there started discovering different, what really made the elements different from each other. And so if you can break a substance down, Then you know into multiple components, then it's a compound. So you have hydrogen and oxygen and water. You can take the water sample, electrolyze it, you get two different substances off of it that you can characterize. That's how you can know that that substance is a compound. And then let's say you have hydrogen, you have an H2 sample. I can't break it down further into different substances. And so then that's when that sample will just be an element. So this chart's a little confusing because you can't really just be handed a piece of matter and go through the questions, but you can be given information or know how a sample was constructed, or really more to the point, just have an idea that you can have mixtures that are homogeneous or heterogeneous. You can have pure substances that are going to be homogeneous in their nature, and the pure substances can be compounds or they can be elements. And then the way you would determine which is just by trying to break those, if they are compounds, down into their substituent elements through chemical reactions. Okay, so let's try this question here for a minute. What term do you think does not describe table sugar? So take 30 seconds or a minute if you want to compare with your neighbors after some thought, feel free. All right, so let's think about this. So does the sample contain molecules? I would probably say so. Now you may be saying, well, how do we know what sugar is? Well, I think most of us probably know the formula of a sugar, if not the compound in table sugar. Does anybody know the formula that's most common in table sugar? You may think C6H12O6, that'd be glucose. Probably sucrose is more common, which would be C12H22. 011. Now you may or may not know that, but that's the formula of sucrose. And so that's one of the major components in table sugar, but it certainly is going to be a molecule. So this is a molecular compound, and it's also a compound because we obviously have more than one element present. I think you would be surprised to find that table sugar was an element. I think that would be really wild if sugar just was one of the 118 elements that we know of, or one of the 92 that actually naturally occur on Earth. So I think it would be kind of strange if it were just an element. And then I think it would be strange if this were anything but a molecule. You know what I mean? Like most of your organic molecules are organic compounds. Most of the pharmaceutical drugs that you encounter are organic molecules. And so they're going to be molecules, not in the category compound like NaCl being ionic. So definitely a molecule, definitely a compound. Now the heterogeneous mixture versus homogeneous. Now it's not saying homogeneous mixture, because we're not trying to say is table sugar one or more components. We're just saying does it look uniform? So when you have a sample of table sugar, does it look the same throughout the sample? I would probably say so, that it's just a white powder that doesn't appear to be in any way any other component in that mixture. So I would certainly say that it's homogeneous. And then the term that would not apply would be, I think that the term that does not describe water is a heterogeneous mixture. And again, this sugar could be more than one component. We're not saying it's not a mixture, we're just saying it's not heterogeneous because I don't see two different phases. I don't see like one layer that could be the one component and a different layer that could be the other. And so I would say that it's not a heterogeneous mixture just from the simple inspection. That would have to appear heterogeneous to be a heterogeneous mixture. And so definitely wouldn't appear heterogeneous to my eyes. And so that's that question. If there's follow-ups on questions, feel free if there's any point throughout the class. Always happy to take questions when they are occurring, because I feel like if you ever are at a moment in the class where something's confusing, let me know, because other people probably have the same question. Now, let's try to describe each box below as either being an atom, a molecule, a compound, or a mixture. In some cases, some of those terms may apply, more than one of the terms may apply. But if we look at box 1, what term do you think best applies for box 1? So probably just molecule, right? Because, and this is something down here that is useful to know, that sometimes when we show these particle boxes like this, we're intending that whenever we show you the same shaded sphere, that's the same element. So the spheres are the same color or shading or assumed to be the same element. Whenever we show you a different shading, like in box 2, if you notice there's dark and light spheres, that in that case, that's implying two different elements. So that these two elements are the same, then these two elements are different from each other. So box 1, because those are the same element, this has to only be a molecule, but not a compound, because we have to have two elements present to be a compound. We have to have two different substances present to be a mixture. We have to have just one atom present for us to call it an atomic gas or an atomic mixture. And so that would just be a molecule. I don't look and say that it's atomic because there's two atoms bonded together. To be atomic, it would have to be a single atom isolated by itself. Box 2, I look at box 2 and I see two different molecules. One of the molecules is a compound. So I see two different molecules. We call that a mixture then. So the word mixture would apply. So I have a mixture of a molecule and a molecular compound. So kind of 3 of the 4 words are applying here. So I have a molecular compound, just a molecule for the other one, and then a mixture when I think of all of them together. So the one word that probably best describes box 2 would be mixture, but it'd be a mixture of a molecule and a molecular compound if you wanted to get really precise. Box 3 is pretty easy, I think. What would you guys would call box 3 well, I guess 2 of the words would apply. It would be a compound or a molecular compound. So the words that are best describing box 2 would be compound, but since the compound's a molecule, you might call it a molecular compound. Then box 4, this is the one that appears where the word atom would apply, so that's an atomic gas mixture. So this would be an atomic mixture. So it might be helium mixed with neon, perhaps. So 2 atoms that actually exist as atoms in the gas phase, they would have to come from the noble gas group. This is maybe something that gets a little complicated, but we're not going to have like hydrogen and oxygen existing in this environment where we have an H atom and an O atom, because this comes up a little bit in chapter 2, that our gaseous elements like hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, iodine, those tend to exist as diatomic molecules in their natural state. I don't know if you should know that yet, but I think it's useful to know that none of the other elements in the periodic table that are gaseous are like the noble gases that exist as just a single atom. Now, why those elements do that is complicated. You may understand the story a little bit if you know Lewis structures and you've seen like hydrogen bonds with itself and kind of pairs up real nice, makes an H2 molecule. O2 does it with a double bond, N2 with a triple bond. We get into that bonding nature in chapter 8. So it's not for a while that we understand the bonding nature, but I'm sure you've seen some of that before and may recall it. Okay, so these types of particle diagram questions are pretty common. Like you'll see some on the practice quizzes, you'll see some in the homework, you'll see some on exams. But just the one thing that sometimes if you haven't seen an example like this, the first time you see it as a test, is the fact that the different shading shows you different elements sometimes catches us off guard. Okay, so in chapter, I think it's section 1.3, they go over a couple of different separation techniques for separating mixtures. And so one of the separation techniques, if you had a mixture that they mention, is filtration. So one of the 3 techniques, if you have a, so imagine you have a container that has a solid in it, and then you have a solution on top. The solution, maybe it's just water, maybe it's some other salt dissolved in water, but you just have some sort of a solid, you have a mixture or a liquid above it, then you can just simply pour that through filter paper. Really easy to filter that heterogeneous mixture. So the heterogeneous mixture here would be a solid mixed with a liquid. And so we can do filtration. Sometimes we do it with a vacuum pump to help us. So sometimes we do something called vacuum filtration. That's just a way to kind of like pull the water more quickly through the filter paper. So you might see this in the lab. I think in one of the opening experiments in the first couple of weeks, you'll do a vacuum filtration step. And so solids can be filtered from liquids and solutions using the technique of simple filtration. So all you need is some sort of a piece of filter paper, something to hold it, and then you just simply pour. And so that's one of our separation techniques. Two of the others, I threw them on one slide because they're mainly educational in the sense that we introduce them here in class. I don't think you'll see examples of these in the laboratory, maybe until you get to Chem. And we don't use too many examples of these, but just to introduce them, because they are in the textbook, I think they're worth knowing these other two common techniques. One's distillation. And so in distillation, you have, a liquid that contains, two substances or more, and then you're gonna heat it up, and then you're gonna take advantage of the vapors containing more of one of the components of the mixture, and then you allow those vapors to then recondense into another container. This is common for ethanol. So this is common that you have some sort of a process where you fermented alcohol. And so if you ferment alcohol, you can get up to maybe 15% alcohol, maybe 20% by alcohol by volume just by that process. But you're not going to get to 80 proof to 100 proof, 120 proof alcohol. That would be 40 to 60% by volume alcohol, or to even close to, as best as you can do, Everclear being what's that, 190 proof. So 95% ethanol is kind of the limit on distillation that you can get ethanol to. You're not going to get to that just by sitting longer in the fermentation process. You have to distill. And so now if I'm distilling water and ethanol, if you knew that water, this gets a little bit just too much into the weeds, but I think it's interesting to see a practical example that ethanol has a boiling point of 78 degrees C. Water has a boiling point of 100 degrees C. So it's two different characteristic properties of those substances. And so if I heat up a mixture of water and ethanol, which of the vapors do you think is going to be more present in the gaseous component above the mixture? Probably the lower boiling substance. Yeah, so we're going to get more ethanol into the vapors. And so we're going to collect a sample that's now a higher percentage of ethanol than what we started with. Now, you generally have to do this more than once, so you have to have a better or a really good type of distillation apparatus that might be really big. But you can do this maybe multiple times, and the best you're going to do, it turns out, is about 95%. But again, the idea is if you have a technique where the substances differ in boiling point, we can take advantage of the distillation technique. The example here shows a salt water, because sodium chloride has a humongously high boiling point and melting point. So if we evaporate the mixture of water over salt, that mostly we're going to get water. But again, we're probably going to have to do this more than once. So a lot of the salt's just going to go along with the ride. So we're going to have to do this a couple times to really get rid of all the sodium chloride. So that's distillation. We can take advantage of that when we're separating a liquid mixture that has two or more components where we get this difference of boiling point. Another technique, you use this a lot in organic chemistry, is called chromatography. It's a really fascinating technique, not one that we talk about too much in general chemistry. It's the technique actually that goes on like if you have a blue ink pen, and you've probably had this happen on a piece of paper that gets wet, if you have a black ink pen and it gets wet, it separates into the purple and blue dyes. I'm sure we've all seen this before. So if a sheet of paper's ever gotten wet using black ink, if you wondered why do you see like a color emerging, it's because you're actually doing a chromatography experiment. You're actually taking the dye that has different colors within the dye, and you're seeing those dyes travel at a different rate through the solid support being the paper. So what chromatography is, it's where we have a column filled up with a material such as like silica gel, picture maybe something like sand or something that's like a solid powder. Then I'm going to pour a liquid through it, and then that sand has like hands on it that are going to hold on to the compounds in your mixture just at different rates. And so if we have a mixture here So here we're going to load a mixture on, it has a couple different components. Those components just flow at a different rate through that solid support. And it's a complicated technique. It's one you have to figure out what solid support you want to use, what type of solvent do you want to use. But you'll see this a lot in Chem. But this is called chromatography. It's just the taking advantage of compounds flowing through a solid support where they travel at a different rate relative to each other. And you can think of this as dyes and ink traveling at different rates through the solid support being paper. So you've seen examples of this before in everyday life. You can use this in the laboratory. There's even a technique, you'll do this in OChem, called thin layer chromatography, where you have like a little sheet of like paper, and you put a little blot of a compound on it, put it in a container that has a solvent to let it travel up, and you'll see the compound separate on that sheet of paper. So it's a very interesting technique. You'll see it more in OChem. Okay, the middle section, I think it's section 1.4 in the textbook, discusses energy. And it goes into a few different examples, and there's really not much that we're going to talk about here in terms of energy other than introducing the idea of kinetic versus potential energy, but sort of relative to chemical reactions. Because I think from a physics standpoint, hopefully we have a good understanding that the bicyclists at the top of the hill would have a high potential energy. If they're not moving, they have no kinetic energy. And then as they go down the hill, they're losing their potential energy as it goes into kinetic energy. I think we have a pretty good model of understanding what that means from like a physical standpoint for a big object. For our chemical reaction, that this is more or less the same situation for water, where water, hydrogen, and oxygen are at the top of the potential hill. That's the bicyclist at the top. They have all that stored energy in their bonds that can then be released as they break those bonds and form new bonds that allow us to form stronger bonds that allow there to be a release of energy. And so this was water going down the hill. As it went down the hill, it was giving off its stored energy into the kaboom. That kaboom was kinetic energy. That was the air molecules moving, being put into motion. And so we saw the reaction lose potential energy as the molecules surrounding it were gaining the potential energy, gaining the heat that was given off from that chemical reaction. And so kinetic energy is the energy of motion. You can think 1/2 mv squared. We don't really do too many. There is an example in chapter 1 of this calculation, plugging in some chemistry examples. I wouldn't worry too much about that. I don't think you're going to see anything like that in the homework or on exams. But the idea here is if you knew the mass of an object, its velocity, you can calculate the kinetic energy. That's like physics class material, if you ask me. The chemistry class material is an object can undergo chemical changes that lead to changes in environment, changes in the bonding nature that allow there to be a gaining or a releasing of heat. So we can have a heat change that accompanies a reaction due to the changes of that potential energy nature. This is what goes on in chemical reactions. The stored energy changing in bonds that are breaking as we make different bonds that are stronger, heat's given off. That's because we have a change of potential energy between the reactants and products. And I just wanted to introduce the idea that you have the same basic framework from physics class as the bicyclists at the top of the hill are the compounds with stored energy that have maybe weak bonds. They react to form strong bonds. We have energy given off. We'll run with this topic more when we get to chapter 5 later. Then as we get through the chapter into section 1.5, we start to get into basically laying the groundwork for some of the math that we're going to use throughout the semester. So of course, introducing some different units, introducing some prefixes that we're going to want you to know so that we can use kilogram or milliliter so that you understand how to use the metric conversion factors. And so there's a couple of metric conversions that I recommend that we know: the giga, mega, kilo, centi, milo, micro, nano. This kind of range here is where I'd like us to know these conversion factors just by kind of understanding which ones 10 to the minus 3. Let's start with the ones we know for sure. So we know that the kilo is the big thing. There's 10 to the 3 grams in a kilogram. So kilo is 10 to the 3. So we have 10 to the 3 grams in 1 kilogram. But if I look on the milli side, this is the one that most students usually know, that's minus 3. That 1 milligram would be a 10 to the minus 3 gram. So a milligram is a 10 to the minus 3 gram. Another way of saying that would be that there's 1,000 milligrams in 1 gram. So we use milligrams for small quantities, because that's a 10 to the minus 3 gram is a milligram. Now centis, 10 to the minus 2. Micros, minus 6. Nano's -9, so we go -2 for centi, -3 for milli, -6 for micro, and then -9 for nano. You could keep going, but we're not going to expect that you know the ones that go past nano. Pico comes next, then femto, and then after that I start to forget. I think it's atto next. But through nano is probably, practically speaking, where if I said nanogram or nanoliter or nanometer, when we get to chapter 6, we'll use that unit a lot, that we'll expect that you know how to use a nanos at 10 to the -9. So 10 to the -9, so 1 nanometer would be equal to a 10 to the -9 meter. And then on the bigger side, it's a little bit easier that we don't have a 10 to the 2 unit that we commonly use, so we just have 10 to the 6 and 10 to the 9. And I just find that, I think if you just know it's kilo, mega, and giga's the bigger one. Like we talked about things in gigabytes, not megabytes, so the gigabyte's the one that's bigger. So this would be 10 to the 9, so 1 gigabyte, or let's say gigameter, we don't use bytes too much in this class, but if gigameter would just be 10 to the 9 meters. So a bunch of meters in the gigameter, because it's a big unit, and then the nanometer is really small, so 1 nanometer, a really small number of meters. And so I would just be able to make those conversions with those prefixes and know that we'll use those prefixes throughout the class. I wouldn't necessarily memorize that there's 7 base SI units, but you may have heard this before, and I think it's worth remembering or kind of understanding why this is important. So there are 7 base SI units. That's the meter being the length unit, mass kilogram, quantity is the mole. If you forget what the mole is, we'll talk about it in chapter 3. We don't do too much with it really at all until then. Temperature is Kelvin. We'll show temperature conversions, if not the next slide, in a couple slides. So temperature is the Kelvin scale. If you haven't used that before, we'll talk about it. Time, seconds. And then the 2 units here, we don't talk at all in this class about these, but the luminous intensity being the candela and electrical current being the amp. Current comes up a little bit in Chem 2 next semester in 1220. So you'll see in the electrochemistry chapter that unit come up. But until then, in this class, we won't actually talk about those 2 units there. But from these 7 units, all other units usually can be derived or defined, one of the 2. And so we have other units that we will use. We have other non-SI units that can be defined or given as well. So we have conversions to other length units, like the inches or feet or whatever, that we can derive and define off of these 7 base SI units. We also have a lot of units that have some underlying connection. Like if you think about energy, if we kind of go back to a minute to the 1/2 mv squared and think about this just for one quick second. Does anybody know the SI unit of energy? I'm sure a lot of you guys know it. The joule, yeah. And so then the joule is connected to the SI unit for mass. The SI unit for mass is the kilogram. Oddly, not the gram, it's the kilogram. And then the SI unit for speed would be meter per second, so meter squared per second squared. So 1 joule turns out to be defined relative to those base SI units of 1 kilogram meter squared per second squared. So anytime you know you have an SI unit, it can be defined off of those 7 base SI units. It's just a matter of how it's done and how it's related. And so again, not putting this up there so that you memorize this as a fact, but just to see that an SI unit is defined or derived, like the joule, off of the, in this case, 3 of those base SI units. Okay, and so we can do some conversions here. So we can convert a quantity of seconds into like megaseconds, which doesn't make a lot of sense to do so, but just to show the conversion, we can do that. We're also asked to write it in scientific notation. I always like to make sure that we kind of, don't skip over some basic arithmetic early on. So like when I'm trying to write this in scientific notation, I like to make sure, because all of us maybe, are coming at this class from a different point and how long it's been since we've seen math and physical science in school. But when I go to move this decimal point over, I'm just going, 1, 2, 3, 4. So this would be 1.25 times 10 to the -4 seconds if I wanted to convert that over to scientific notation. And so if I want to convert that to megaseconds, and again, this won't make a whole lot of sense, on why we're converting this, but this is just to use the unit to see a couple examples. If I want to convert that to megaseconds, and again, I'm going to make sure to show early on dimensional analysis is a tool. There's a couple slides later on it as a defined topic. As topic in the book, I think it's section 1.7 is using dimensional analysis, but that's that method where we can just try to be really, clear on writing out our units and then trying to write out our conversion for seconds into megaseconds. So when I'm making this conversion here, I'm just trying to think, well, what's the conversion between megaseconds and seconds? That's the correct definition. And the easy way to make a mistake is to say, maybe 10 to the 6 megaseconds per second. You see how that would be wrong? That it's either going to be 1 second is 10 to the minus 6 megaseconds. So 1 second is a really small amount of megaseconds. That's probably not always my first thought. My first thought here, since that's the big unit, is that 1 megasecond would be a 10 to the 6 seconds. But the easy thing to mix up is put 10 to the plus 6 on the top or put 10 to the minus 6 in the numerator side. So just making sure you have a good thought that there's a lot of seconds in a megasecond, and then that should hopefully get us onto the right side of making sure the 10 to the 6 is on the right side. And so then that we can put it into a calculator. The one thing I sometimes like to mention is be careful with the E button versus like the 10 to the caret button. So if I'm putting this into a calculator, I'm either going 1.25 divide by 10 to the power of 6. I see a lot of times students will take their calculator and do like 10e6. So like imagine you have your calculator and let's do 1.25. And again, some of you may be saying, why am I showing you or reminding you that it'd be 1.25 e to the minus 4? Again, it might be a while since we've seen or done this into a calculator, but I go e to the minus 4 to enter. And if I go divide, I don't want to divide by 10e minus 6. That's not the right calculation. I either want to divide by 10 to the power of 6, or I might even go divide by 1e to the 6. And then if I flip it over, it should show me 1.25 times 10 to the minus 10. And of course, you'd be also sitting there saying, well, you're just dividing by 10 to the 6. 10 to the 6 is just going to go to 10 to the minus 10. You could do this math without a calculator very easily too. And so this should be 1.25 times 10 to the minus 10. And if you think it's minus 11 or minus 9, we're probably just putting that 10 to the minus 6 incorrectly into our calculator. And if we go to microseconds, this just flips the minus 6 around. So for converting this to microseconds, so if I think again, I'm just making the conversion. I just want my unit to cancel. I didn't show this here, but I just want the seconds to cancel. So I'm dividing by seconds. And I want to convert that into microseconds. And then how many microseconds is in 1 second? There's going to be a lot. So this would be 10 to the plus 6 microseconds, a lot of the little unit in the big unit. Or I could say that 1 microsecond is 10 to the minus 6 seconds. And so then this should lead to 1.25, I think, times 10 to the 2, but let's do the math to make sure. 1.25 e to the minus 4 times, now I just do 1e6, or you can do times 10 to the power of 6. That gives me 125. And then nanoseconds just takes it one more unit, and nanoseconds 10 to the minus 9 to cap that off. Let's do it the other way around here. Let me say, well, how many seconds are in 1 nanosecond? 1 nanosecond is really small. This might be where I'm using this unit here. That's 10 to the minus 9. So 1 nanosecond, 10 to the minus 9, or 1 second, 10 to the plus 9 nanoseconds. Same conversion factor no matter which way you use it, as long as we're not mixing up where that minus sign is here. And that should be 1.25 times 10 to the 5, I think. Yep, 1.25 times 10 to the 5. Okay, so that's a couple conversions. We'll start off next time with some temperature conversions and get into our favorite topic, significant figures. So we'll see that on Monday. Have a great weekend, everybody.